Okay, so you can see our objectives for today. We are going to be learning how to calculate speed, which should be a refresher for you because we did it some in the lab, but we didn't explicitly talk about how to do it. Then we're also going to describe what acceleration is, and then we're going to determine what causes acceleration, because that's one of the big important pieces, okay? So to begin with, we're actually going to start off with a mini lab, okay? So what you're going to do is you're going to, as a class, come over here to the courses that I have laid out, okay? And note the different markings that are on the floor. So yes, unfortunately, I know it's early. This does mean you have to get up out of your seat. Okay, so we walked the courses, the two different courses, and you should have noticed that they felt slightly different, right? Okay, and that's on account of in the first course, you were traveling the same distance every 2 seconds, okay? In the second course, the distance you had to travel increased, but the amount of time you had to travel it in stayed the same, okay? So this is meant to model for you acceleration. So what we're going to do now is we're going to fill out these charts together, okay? So to begin with, at time 0, we were at what distance? 0, right? So you could put 0.00, however you want to do that. And it's measured in meters. Okay? So we had not moved. At the first time, we were at the first mark, and since this chart that we're filling out is for the first course, you had traveled half a meter. So you can put 0.5 meters for your distance at second 1. Okay. And then at 2, you were at 1 meter. At 3, you were at 1.5 meters. At 4, you were at 2 meters. And at 5, you had gone 2.5 meters. Okay. So those were your distances. I measured them out when I put the tape marks down. So to calculate our speed is equal to the distance traveled divided by the time it takes to travel that distance. So between 0 and 1 seconds, how far did we travel? .5 meters, right? We went from being at 0 meters to 0.5 meters, so we traveled 0.5 meters. And I was clapping every 2 seconds, so it took you 2 seconds to get there. So we would take 0.5 divided by 2. And somebody want to do that on their calculator for me? I always mess up these little math problems like this. So 0.25 meters per second was our speed, which makes sense, right? Every second we went a quarter of a meter. It took us 2 seconds to go half a meter, so makes sense. What distance did we travel between 1 second and 2 seconds? Also 0.5 meters. So that means our speed should be the same, right? So, I put this in the wrong spot. I meant to put it up here. And then here would be 0.25. And so you can begin to see the pattern because we were traveling the same distance and over the same time, our speed actually winds up being the same for the entirety of the first course. Okay, we wound up traveling at the same speed. Okay, so what you experienced on this course is because you were walking at the same speed the whole time, you didn't experience any acceleration. You did not speed up and you did not slow down. So we would say while your speed was 0.25 meters per second, your acceleration was 0. Okay. So on the second course that you ran, at 0 meters, or 0 time, what was your distance? 0. You're correct. Still 0. Okay, because we're still at the very beginning. And when you went to 1 second, you had traveled 0.5 meters again. Okay, so the very beginning of this is like the start, which makes sense. You can see that the lines line up, right? Then between marks 2 and 3, so you were at half a meter at 1 second, and then you were at 2 meters by second number 2. I'm trying to remember what I did here. No, you were at 1.5. That's my bad. Okay, so you went half a meter, then you were at 1.5, then you were at 3 meters, and then you were at 5 meters, and there wasn't a fifth distance for this one. Okay. Now, we'll remember our speed is equal to distance divided by time, and that our time is always equal to 2 seconds, because that's how often I was clapping, right? So, our first speed will be the same as it was in the first experiment, because we went half a meter in 2 seconds, and we already did the math on that, so we know we went 2.5 meters per second. Okay. But here's where we get into the tricky part. How far did you travel between times 1 and 2? If you were at 0.5 meters and then you were at 1.5 meters, you traveled 1 meter between times 1 and 2. Because you were at 0.5 and you made it all the way up to 1.5. So you just added a meter to your distance. So that means you had gone 1 meter, and 1 meter divided by 2 seconds is 0.5. So your speed now was at 0.5 meters per second. For this next one, you went from 1.5 meters all the way up to 3 meters. So how far did you travel there? Well, you're going to take 3 minus 1.5, and you'll come out with 1.5. So you went 1.5 meters in 2 seconds. So divide 1.5 by 2, and you'll have a speed of 0.75 meters per second. And then for the last one, you went from 3 meters to 5 meters. So take 5 minus 3 and you get 2. And 2 meters divided by 2 seconds, you're going to come out with 1 meter per second. So for this one, what I want you to notice right here is that every 2 seconds, your speed is increasing, right? Because you had to travel more distance in the same amount of time, so you had to move faster. This is what we call acceleration. It's one of the forms of acceleration. So, now we're going to take a look at what constant motion, which was course 1, and acceleration, which was course 2, looks like on a graph. Okay. Our next page is just a graph, nice graph like this, okay? And we're going to plot time versus speed on our graphs. Okay? So let's do time along the bottom of this. So let's do every 2 boxes is 2 seconds. So we start at, oh, I forgot to turn my writing tool on. It moved forward. We start at 0 seconds, right? And then at 2 boxes, we put a 2, and then a 4, and then a 6, 8, 10, 12, I don't know exactly how far up we need to go, 14, okay? And then we'll just go up the side in increments of, we'll do 0.25s, okay? So this is our speed in meters per second, and this side is time in seconds. So we'll do 0.25, and then 0.5, and then 0.75, and then 1, okay? And that's every 2 lines as well. I just didn't draw it super neat. Okay, so for our course, for the very first one, how fast were we going at the first time interval? 0.25. So then we're just going to go ahead and put a dot at 0.25. What about at our second time interval? Same thing, 0.25, right? Go away, little selection thing. Okay, what about at our third time interval? Fourth? Fifth? Yeah, so you can see that the graph of this would then be a line, right? And I made it tip up at the end, but I shouldn't have. Okay, so when you see a straight line like this on a graph for speed versus time, that means that there was no acceleration because the speed stayed the same. Okay. Now, what would happen if we did this for our second course with the same time markings and the same speed markings, okay? So for our first time marker, what was our speed? 0.25, okay? What about for our second one? 0.5. Our third one? 0.75. And our fourth one? 1. Okay, so this one, the graph goes up, right? And so that's a good example of what a graph looks like when you're plotting something that's accelerating or speeding up. What might this line look like if we were slowing down? Yeah, it would just tilt in the other direction, right? It would be coming back down. The speed would be getting lower as the time kept going on. Good. Okay. So now we can actually jump into the part of this that's notes. In the lab, you experienced acceleration, which we define as the rate at which velocity changes. When we mention velocity, velocity is just speed, but it also includes a direction. So if you can include the direction you're traveling with your speed, then you have a velocity. You can accelerate anytime you change your velocity. So that means there's 3 different ways you can accelerate. And those ways are to speed up, like we did in the lab, to slow down, like your cart did when it didn't have its propeller turned on, or, and this is the one that often surprises people, by changing your direction. Okay, so even if you keep the speed of your vehicle constant, if you turn around a corner, you're technically accelerating because you are changing the direction of your velocity. On the first course, your speed didn't change. You kept your speed the same the whole time, which means your acceleration would have been 0. But in the second course, you sped up, and we could calculate your acceleration by taking the initial speed, the final speed minus the initial speed and dividing by time. But the important thing for you to remember is that when you're speeding up, that acceleration would be a positive value. If you're slowing down, oftentimes those accelerations are listed as negative numbers. Your speed is technically changing, but it's getting smaller. In order for an object to accelerate, there must be a force acting on it. Objects don't just speed up or slow down or change direction on their own. There has to be a force involved. We define a force as any push or pull that affects the motion of an object. Okay? So I want you to consider Newton's second law of motion. Okay? Newton's second law of motion says that force is equal to the mass of an object times that object's acceleration. Another way to write this is that acceleration is equal to the force divided by the mass. So if you want your acceleration to go up, you must increase your force. And vice versa, if you would like your acceleration to decrease, then you need to reduce the force. Now consider the cart from the propelling a cart lab that we did before today. Okay? The only force on this cart is the force of the propeller, correct? When you turn the propeller on, you didn't also push it, right? And there's no one pulling it or blowing on it or anything. So the only force is the force of the propeller. But is the propeller pushing on the cart? No, the propeller isn't pushing on the cart. The only thing the propeller is touching is the air. So if the propeller isn't pushing on the cart, then how on earth is it making the cart move? Well, what this comes down to is Newton's third law of motion. Newton's third law of motion says for every action, there is an equal and opposite reaction. And this has to do with forces. So for every force, there is an equal and opposite force. So a force that's equal in strength, but opposite in direction. When the propeller of the cart pushes backwards on the air, then the air pushes back on the propeller. And since the propeller is attached to the cart, then the force is also applied to the cart and the whole thing moves. I promise to come back to this screen. I'm going to move off of it for a second to draw you a picture, but I will be right back to it, okay? So you have your cart, right? And you have your propeller at the top. We're looking at this from the side, so the blades go kind of like this, right? And as they spin, the blades push back on the air, okay? And then the air pushes on the propeller with a force that's equal in strength but opposite in direction. And when the air pushes on that propeller, then the whole cart moves forward because the propeller is attached to the cart. If the propeller wasn't attached to the cart, then the cart would not move. The last thing I want to talk to you about is a thing called momentum. It's something that all objects that are in motion have. Now, you may have heard the word momentum used to describe maybe a sports team. So if somebody says a baseball team has a lot of momentum, what do they mean? What do you think? Someone describes a sports team as having momentum. What are they trying to say about the sports team? They're good, okay? Are they going to be easy to beat? No, right? So if they're describing the team as having momentum, they're saying, hey, that team's going to be hard to stop, right? You're going to have a hard time beating them because they have momentum. Well, when we talk about objects having momentum, we also are describing how difficult it will be to stop them, okay? An object's momentum is calculated using the formula momentum is equal to the mass of the object times the velocity of the object. Okay? What this means is if two objects are traveling at the same speed, but one of them is way heavier than the other, that object will have more momentum. This makes sense to us, right? If I rolled a basketball and a bowling ball at you at the same speed, which one would you have a harder time stopping? The bowling ball, the one with more mass. Okay? And if I take two objects with the same mass and I throw them at you with one with much more velocity, the one that's moving way faster is going to be the one you are going to have a harder time stopping. Okay, so the more massive an object is, the greater its momentum, of course, if the velocity of the two objects is the same. In order for velocity to change, we know that there must be a force experienced by that object. And what that means is that in order for the momentum of an object to change, you must also have a force involved. Okay, so that's why we talk about momentum as how difficult is it to stop. If something has a lot of momentum, the force required to stop it will be very big. If something doesn't have a lot of momentum, then it will not require as much of a force to stop it.